So now let's look some application domains where those principles, yeah, mapping, DVFS and partitioning can be applied to do some sustainability, yeah, which means kind of improving the energy efficiency or increasing the lifetime. Okay. What are those application domains? So one of them is multimedia applications, yeah. So you know, multimedia is like lots of image processing, video processing, listening to music and all those kind of things, yeah. Again, this has to be run onto some infra platform, and this could be like a multi-core platform, yeah. Let's say if this is our smartphone, right, this is, we saw the architecture, yeah, like the multi-core or many-core architecture that can be in a smartphone, yeah. So this can be inside this, which means if you are watching a video, you are taking a photo, or you are listening to some music, or you opening a browser, so some task will run in some of the cores, right. And now you know, with those options, mapping, DVFS and partitioning, you have lots of choices, right. You need to kind of decide which, if the browser application opens, which core it will use, or if it is a kind of multi-threaded application, which 2 cores it will use, or which 3 cores it will use. And also it's going to compete resources with other applications. Okay. So mapping is going to play a lot of role, and if each of these cores supports voltage, different voltage frequency levels, so you need to decide like how much workload that core has, and then decide which voltage frequency it should use, yeah. So in that process you can save power, yeah. So what typically you have to do, like I said, you load the tasks on the resources, and also over the time you adopt, yeah. It's not like if you put your browser maybe on these 2 cores, you should not always keep on the same, yeah. It could be in future there are lots of applications running, then this core might need to be shared by other application. So maybe you need to move things on one core for one application. So over the time, depending upon what is running, you need to adopt, yeah. And when you are doing this, you can try to meet lots of objectives, yeah. Could be the timing, performance, it could be about energy efficiency, it could be like you are trying to balance the temperature of the smartphone, right. And you can also try to meet some security objectives, yeah. Okay. So security one, I think at the moment when you do resource management, it's not done a lot in smartphones, but if you remember I said there are upcoming architectures, they say there is like a secure zone, this non-secure zone, right. So if there is kind of a like a banking application, yeah, we have lots of banking applications, right. So you can decide those kind of things always run in the secure zone, yeah. So it will have its own memory and everything, so whatever like the password, everything is cached, nobody else can see, okay, if someone gets access of your device and tries to do reverse engineering. Automotive is another case. Remember we said there are like hundreds of electronic control units, right. These are simply microcontrollers or processors, okay. So these are distributed, and if you remember I said they are connected by a CAN bus, yeah. So again, during different time what the car is doing, there is a lot of tasks going on, so you can decide which task is going to run on which core. In the car there is no dynamic voltage frequency scaling, yeah, everything is running at the same frequency, so only the mapping is the main part, yeah. And in car the most important metric is the timing, yeah, because it's very critical system, okay. It could be applied in server and cloud computing systems as well, yeah. So how typically servers are designed, or HPC platforms, so you have several nodes, yeah, and each of the node is like a server that has a processing elements and they are connected somehow, and then each of these nodes or servers are managed by a kind of entity called platform resource manager, yeah. And that platform resource manager is basically kind of running on another server, but that is like monitoring everything, yeah, rest of them. So if that's the situation, then basically it can keep getting lots of jobs from different users across the globe. Yeah, like there are many people who use Google's data center. Yeah, many people are using OpenAI's data center, so they are requesting lots of jobs, right? It's like everybody is typing into ChatGPT to get a lot of answers. So lots of users from lot of places, but then they are going to decide basically from where exactly they need to match, yeah, the answers. Okay. When you are doing that, you can have several aims, right? And one of the aim could be energy, yeah, like reducing the energy cost of the data centers. There is another aim, value. Value is basically the profit or money for those companies. So when they are doing that, this is their first aim, like they want to maximize the profit. Okay. Later on we will see like what it means. So profit typically means you try to complete application as soon as possible. So for us it doesn't matter, but there are like the banking companies or some other companies, they give the task to these data centers and there is a pricing model. They say if you finish my task in 1 hour, this is the money you will get. If you finish my task in half an hour, you get more money. Yeah. So there is a time and the kind of value curve, it is like this. Yeah. So you take more time, you get less money. You finish fast, you get more money. I think because these banking sites have to kind of decide the next day or within a couple of days next steps, yeah, whatever transactions has happened and all those kind of things. Yeah. So you get that kind of money. Yeah. Even this kind of thing can be used basically for like the social media companies, right? They look for a lot of users what you are doing, based on that you get some ads, right? Sometimes you have accessed something, you get some ads. Yeah, but these companies are not doing just for one person at a time. So they're taking whole data from all the users and then they are trying to analyze all the data and throwing you the ads. Yeah. So similarly this can be done. Throughput is again like how many applications you can finish within certain time. So the aim is always to get the highest throughput. Yeah. I mean there are some research where people have tried security optimization as well. Again, kind of defining like some of the servers are maybe more kind of handling more sensitive workload. Yeah. So putting the workload into that. Okay. Okay. Now I have a question. Can you think of any other application domains where you can apply similar kind of optimizations? Yeah, it's basically mapping, DVFS and partitioning. Yeah. Okay, I think I need to switch to that screen. So we saw multimedia, the cloud and then automotive. Yeah. Anything else you can think of? Do you see it? Okay, I see it now. Okay. No? I would say like wherever you have a processor, yeah, and there is not a single microcontroller, you have more than one, yeah, and if some of these or each of these support this dynamic voltage frequency scaling, yeah, so it can be applied any of those places. Yeah. So those three I said you mentioned, this is the kind of application domains I have considered in my research, but there could be many others as well. Yeah. For example, it could be like some kind of in medical field as well. Yeah. Let's say they want to discover some new drug or something. I told you the example. Yeah. Or some people are taking lots of images of something that, I mean, imaging is one of the ways to drug discovery. Yeah. So what they do is like they put some tissues, they put some kind of you can say chemical on the tissue. Then over the time they observe what kind of changes are happening, and every second they take like hundreds of images. They are like high-speed cameras, and then these images are going into a computer and then they process. So again, if the application is coming from medical domain, but the platform at the end is this, then basically the same thing can be applied. Yeah, they have like millions of images. Then again you have to decide on which server which one should be going, and then how they will be processed there. Okay, yeah. So medical is another one. Manufacturing and control systems again could be interesting. So let's say in manufacturing you have again lots of microcontrollers at different places, yeah, to monitor or to take some actions. So depending upon what it has to do at different points, again if it supports like different power modes, you can make it up, make it down. Yeah, maybe there's manufacturing pipeline, right, and there are so many stages. At the last stage maybe nothing is going, or something will reach after 1 hour. Then you need to turn those electronics, you do not need to turn those electronics, yeah, until things reaches there, or it needs to be processed. Yeah, okay, good. So medical, manufacturing, yeah, these are other two. Okay, now these the things we are doing, right, these controls, in a way we are trying to optimize something. Yeah, we are doing it to optimize timing, energy, or security, something else. And if we take these methodologies that basically exist in the whole literature, we can classify them into two categories. One thing we can say is design time, and this one is for a static workload. Yeah, another one we can say is run time, that is for more dynamic workload. So static workload is like, you know, this is the application, there will be no other application that is going to run. Yeah, so for example in a smartphone, yeah, remember long back you could only call, yeah, you could only just play few games, maybe snakes, ladder, those kind of things. You knew there are just few applications you can run. Yeah, so that is a more static scenario. Now it's very dynamic. But if it is static, you kind of know what is the platform, what is the workload, you can do the optimization in a different way. Yeah, but if things are changing a lot, those things will not be applicable. Yeah, so now we are going to look some of the design time optimization approaches from the point of view, again we want to touch sustainability, so we want to reduce basically energy consumption. Okay, and then we will look some runtime. Okay. Okay, so for design time, so like I said, you know the whole workload, you know the whole platform. Yeah, so you can perform optimization with a global view. Yeah, so it's like, you know all the situations, you can find the best mapping or best operating DVFS points or best partitioning. Yeah, because there is no other application that is going to come. So it's always the same. Okay, and this one will result normally in a better quality of results. Yeah, because in comparison to runtime, that where the situation is always changing, so it's not easy to get the best results. Yeah, and there is a huge literature that falls under this design time optimization categories. Okay, so let's look some of these literature. So these are literature are also kind of classified into different well-established search approaches. Yeah, like simulated annealing, taboo search, integer linear programming, genetic algorithm. There are many others. Yeah. Out of these, so you can think like, let's say you have a phone and then there is a task like multimedia, and that task may have maybe 10 processes. Yeah, and then your phone has 8 cores, so those 10 processes has to run on 8 cores. Yeah, again there are so many possibilities. Yeah, you can use 1 core, you can use 2, you can use 3, but if you're using 2, which 2, if you're using 3, which 3, so many possibilities are there. Yeah, so to kind of discard some of those possibilities that may not give the best result, you know, so there are some approaches called like pruning. Yeah, so that you can get the best solutions or best operating points as quickly as possible. Otherwise, sometimes it may take like whole month if your, like, let's say in your platform number of cores are 1000, yeah, and if you are like 10 applications each with 10 processes. So there are approaches that apply, pruning approaches, yeah, pruning strategies. So simply means you don't need to evaluate all of the possibilities, okay. That's a way to discard some of the possibilities. Okay, I think I have a question after this. So do you see any disadvantage or disadvantages to prune the search space? Okay, let's see this view. No, good. The good part is you can get the best solution in less time, yeah. And I do not have much time, but in one of our research we have shown like you sometimes need a month to, if you are exhaustively exploring all the possibilities, because possibility simply means take the task, put on the core and evaluate how much time it will take and how much energy it will take, yeah. Then do the same for other possibility. And again, each of these possibilities you have to also evaluate. A core is running at certain frequency, yeah, another frequency. Evaluate all these possibilities, and then that takes a month or something, yeah. May not give 100% accuracy. Maybe you want to say efficiency, yeah. So it could be, if you are pruning, there is a possibility you can basically discard some of the points, might be that one was good, yeah. So it can happen, yeah. So that means less efficient, yeah. So there is a possibility you can miss some kind of nice points in this process, yeah. But like I said, you cannot explore all the design space within a limited time. So this is typically a practice, okay. So I would say there is some disadvantage, yeah. You may miss some design points that are useful. Okay, so I am just saying here one example of like exhaustive DSE. Exhaustive means evaluate all the possibilities, yeah. So now let's say like your mobile phone, yeah, you need to run maybe hundreds of applications, yeah. You take your architecture, that is the chip that is in your phone, and you take the exploration matrix, like what you want to achieve, yeah. Maybe you want to take less energy. So for each of applications you will try to find lots of options, yeah, like there are a lot of possibilities to use different kinds of cores, and then if you use GPU it can be partitioned as well. So even just for one application this can be millions of possibilities. Similarly for another application. So imagine in a phone, if you want to do for hundreds of applications, this can be many billions of possibilities, and you cannot evaluate all of these, okay. That is why the pruning is applied, okay. All right, what's the time? Should we break now? Oh no, we have 2 minutes more. Let's look this one. So if you remember, I said there are well established search approaches, right? Turbo search, integer linear programming. I also said about genetic algorithm. So this one is very, very popular, yeah. So you can say genetic algorithm is again like bio inspired approach, yeah. So we are going to look this with an example, and we will look these two aspects, basically mainly these two controls, yeah, mapping and DVFS, okay. And the example that we will look is this autonomous, not autonomous, but automotive vehicle, yeah, basically a car, yeah. So we have already seen something like this, like a car has several electronic control units, and here it's about more detail, like these electronic control units are distributed across different sections, yeah. One is powertrain system, safety systems and comfort systems, yeah. And these are again in 100, yeah, like 100 to 200, okay. And out of these, the engine control unit, yeah, is the most complicated electronic control unit, and this belongs to powertrain system. So basically the electronic control units that are near the engine. Okay. So we are going to basically look the tasks typically that are running in the engine control unit system. Okay. So here I am going to show a kind of demo car example. Yeah, in a real car there will be so many tasks. Yeah, maybe thousands or maybe millions. Yeah. So this one demo car is minimal functionality gasoline engine control unit. Yeah, that means this is like a toy car. Yeah, it's not a real car example. Yeah. So you can see this is a complex graph. So in the engine control unit there will be like, these are the tasks with the squares. Yeah. So these are the tasks, and when they are running they will exchange some messages from others. Yeah. So here you will find like there are total like 18, actually in automotive terminologies these tasks are also called like runables. Yeah, it's just the domain change, things change. So there are 18 of these boxes. Yeah, that means 18 tasks are running. Okay. Automotive, like I said, these are called runables, and task definition is slightly different. So you can see some of the runables are with the same color. Yeah. So essentially they are doing more or less the same task. So it's like for one task there are two processes. Yeah. So the runables can be processes here. Okay. So 6 colors you can see. Okay. And there are 61 labels. So those are basically just the edges. Yeah. The way they are communicating. So labels is called like, let's say there is a need of communication from here to here. So there will be a buffer or something. Yeah, to hold the data. Okay. So this is the demo call example with 18 runables. Okay. Now what will be the design time DSE? You want to take this kind of application, yeah, with 18 runables, and you want to take a multi-core platform. Yeah, these are like 6 cores, and then you want to map on this. But again, like I said, there is huge possibility. Yeah, so you can do some design space exploration to come up the best with the best possibility, or some couple of them. Yeah, to decide on which one is the best. Okay. And when you are doing this DSE, you are trying to come up with the possibilities. One thing is you can do exhaustive, yeah, evaluate all of them, but that's not possible with the limited time. So when you are going to come with some limited set, you have some aims. Yeah, what could be? It's like you want to find all the possibilities. There is no deadline miss, because car is a very critical system. Yeah. Like I said, brake has to be applied within microseconds, so that deadline should never be missed. Okay. There could be some other goals. You want to use minimum resources. Yeah, it's again for sustainability. Yeah, and you also want to reduce the energy consumption. Yeah, so if it's car, basically now if it is EV, you can enhance the lifetime. Yeah, like you don't need to charge the battery again. If it's data center, again you are reducing the energy bills. Okay. So this is what basically can be the goals. In the next one I am going to kind of explain how the genetic algorithm can be used to get the best design points, yeah, by which we can operate. But before that, let's have this break. Yeah.